In this video, we're going to be covering basic theories that you need to know when doing engine performance work on a car. We're going to be covering atoms, elements, compounds, molecules, parts of the atom, Newton's law, work and force, energy and energy conversion, inertia, momentum, aerodynamics. We're going to take a look at friction, mass, weight, and volume, power, compressibility of gases, and non-compressibility of liquids. We're going to go through most of those fairly quick because they're not real critical. At least most of them aren't real critical. However, you can see the atmospheric pressure and vacuum. That's going to be a really critical one to understand. Just real quick to begin. Atmospheric pressure at sea level averages 14.7 psi. It is based on the gravitational pull of the atmosphere, which means the weight of the atmosphere at sea level is 14.7 pounds per square inch. When you watch the news, they will talk about the barometer is dropping when there's a storm coming in. The barometer dropping means this pressure is decreasing. The 14.7 pounds per square inch is average. As you start going up in elevation, means there's less atmosphere above you. Atmospheric pressure is going to decrease. We're also going to talk about Venturi vacuum, and just real quick right here, if I have air flowing through at a certain velocity, when it gets to the smaller pipe, in order to move the same volume of air, it has to move faster. As it changes from that slow to fast, it's going to create a low pressure area, and that's what this tube right here is showing you. They have a brown liquid in here. You can see with the lower pressure, it came up higher on this side because the higher pressure over here is pushing down farther. Inches of mercury would mean that this was filled with mercury. They would both be even at this point right here. As you put a low pressure on one side, if this came down 2 inches and this one went up 2 inches, that would be 4 inches of mercury. You can do the same thing with inches of water. But the weight of water is way different, so it's a totally different scale. And we're going to talk about combustion a little bit on this. We'll get it more in the later one. And then we'll talk about basic gear theory. Atom, smallest of the chemical elements. The elements are solid, liquid, or gas. The compound would be like water, where it contains hydrogen and oxygen. The protons, neutrons, electrons, all I want to care about is electron, because with electricity, that is the movement of the electrons. Ion is an atom or molecule with an electrical charge. The place we're going to be dealing with this is if you look at a secondary ignition pattern, you'll see a high voltage to initially get the spark to jump across to the gap. Once that spark jumps across there, it ionizes a trail. So the current will continue to flow as long as there's enough voltage in the coil, but it requires a lot less voltage once that trail is ionized across there. Then we have acids and bases. I've been working in the industry since 1980, and I have never once stopped while I'm working with something to wonder, is this an acid or is this a base? Newton's law of motion. Taking a look at the first two. A body at rest wants to stay at rest. A body in motion wants to stay in motion. Bottom line here, what is going to require more energy? To get a car move up to speed from its standstill, or to maintain that speed? Obviously, it's going to be the acceleration. When is an engine going to work harder? During acceleration or during cruise? When are you most likely to have engine driving problems? And obviously, it's during acceleration when the engine is working harder. The third law is the equal and opposite force. And on this one, we're going to have air pressure that is going to be fighting against the car moving, wanting to slow the car down. And we'll also have the friction of the tires on the road. Work as opposed to force. Looking at these two images down here, you see this guy pushing on this big rock, and even though he's pushing, it's not moving anything. So he is applying force, however, there is no work that is being done. On this one over here, they move their smaller rock X number of feet in a given amount of time, and you can use this distance, the weight, and come up with a calculation of work. The work that we're going to be dealing with is horsepower. That's based on work that is being done. In Europe, they don't use horsepower, they use the kilowatts, and we'll talk about that. We will also be dealing with torque, which is a twisting force. We have potential energy, which is energy that is just sitting there waiting to be used. That's going to be our battery with a chemical energy inside of there. It's also going to be gasoline. that has a chemical energy. The kinetic energy is when it's being released, as we change the chemical energy to electrical energy from the battery, or when we burn our gasoline, we're releasing that energy. 7 common types. Chemical, again, that's the battery or the gasoline. The electrical, when we have our electrical energy to mechanical energy, that's our motor. The chemical to electrical was at the battery. We also have the thermal. Our gasoline, when we burn the gasoline, it is going to convert to a thermal energy. The thermal energy, as it's expanding, is going to change to mechanical as it pushes down on the piston. As the piston's connected up to the crankshaft converts it to a rotary motion. If we turn the alternator with that, then we're going to go from mechanical to electrical. We're also going to go from mechanical to thermal with our brakes. Radiant, I left it in here just because as I was reading it, it's included electromagnetic, and I thought, oh, we've got electromagnetic, but then I realized, oh, magnetic radiation. No, we're not using magnetic radiation on the car. We're also not using nuclear. If we ever do have a nuclear-powered car, I think I will stop driving at that point. Solar, yes, we do have some solar panels, some solar transistors, solar diodes that are on the car, but they don't do a whole lot. I mean, they work good as a sensor, but as far as using light to create electrical energy, they're not efficient at all. So even if you covered the entire top of your car, you'd be fortunate to get 10 to 15 amps at 12 volts from that. When you look at an electrical vehicle where they're looking at hundreds of amps operating at 100 plus volts, well, 10, 15 amps at 12 volts, that's relatively insignificant. Inertia, static, it's at rest. Dynamic, it's in motion. On the dynamic, as we're moving the car, it's going to have the wind resistance, the rolling resistance, and then we also have the brakes if we're trying to stop that. If we want to gain momentum, we're going to be using the torque from the engine to get it moving. Losing momentum is going to be braking. If you have a diesel engine, you can compression brake. If it's a gasoline engine, you can vacuum brake. If you have a hybrid or electrical vehicle, we can do the battery regen, and that's where the motor that was accelerating it now switches and it's a generator, and we're slowing the car down, converting that energy into electrical energy to recharge the batteries. And then we have our disc and drum brakes for mechanical. Our tires to the road, the stickier, the larger tires are, it's going to affect economy. However, we have to have a certain amount of stickiness to the tires, otherwise we're just going to spin the tires and not go anywhere. With the air, and I looked this up, I found this was interesting, that depending upon the vehicle, how aerodynamic that vehicle is designed, somewhere between 20 to 30 miles an hour, most of the power required to move the car is overcoming wind resistance. The more aerodynamic the car is, the higher that speed would be. Liquid also has resistance to it, not resistance, but friction to it. And you've probably noticed that if you were driving along and hit a puddle of water, you can feel the car suddenly slow down. Coefficient of drag. They're trying to make the cars as aerodynamic as possible. They've been doing this for decades now. I have heard the complaint that, man, all the cars look the same because the cars are being designed in a wind tunnel. If you go back and look at pictures of cars from the 50s, so if somebody shows me a car, I can pretty much tell what decade it comes from. So to me, that's always been true. But people complain about it more now. I found this picture on the internet of wind tunnel testing, and this is really good because they're showing you some sort of gas in here that fluoresces in this wind tunnel test, and you can see how the air is moving around this car. They're trying to get this to be as smooth as possible. You can see where the turbulence happens. So one of the places is right here at the mirror. You can see it becomes real turbulent. Manufacturers spend a lot of time designing the mirror to decrease this amount of turbulence. You can also see it behind the wheels. This wheel tire is going to create some turbulence. I read this one article on some guys that were making aftermarket Tesla parts, and they changed the wheel on the Tesla Model 3, and they did one other change that I don't remember what it was, but they actually got an improvement of 5%. So they were able to drive the vehicle 5% farther on a charge with changing the wheels, that was the most significant change of making that more aerodynamic. You can also see under the car, you get a lot of turbulence under here. The manufacturers try to make that smooth. If they have a full active suspension, the manufacturers will sometimes lower the ride height of the vehicle as vehicle speed increases to decrease this turbulence under the car. Now that we are using scroll type compressors, which draw 1/3 the horsepower to be able to do the same amount of work, there are some aerodynamic vehicles out there that you can actually get better fuel mileage running the AC and keeping the window rolled up than you can with turning off the AC and rolling the window down and having it act like a parachute to slow you down. Mass, weight, volume, bottom line is the bigger, the heavier the car, more power it's going to require to move that vehicle down the road. So if you want fast, good fuel economy, smaller, lighter car. Torque, which is our twisting force. Again, I can apply torque without having any movement. This dot right here is the center where I'm going to be applying this torque. If this is 1 foot out, if I push at this point A with 50 foot-pounds, then right here I'm applying 50 pound-feet of torque. If you come out 2 feet, so through this point B here, and again if I push with 50 foot-pounds, that's going to be 100 foot-pounds of torque because I have the additional leverage. Make sure that you remember that, because when we get to talking about the engines and we're talking about increasing torque from the engine, this is going to be a factor. Can we get more torque at the wheel than we can from the engine? If you say no, then the transmission is useless because they're using the transmission as a torque multiplier, meaning I can get more torque at the wheel. It comes at the price of speed. So the greater the gear reduction, the slower I'm going to go, but I can get more torque. On an overdrive, it's going to be just the opposite. I can get more speed, however, it's at the price of torque. This one, 1 horsepower, 33,000 foot-pounds per minute. And they're showing you here this horse lifting 33,000 pounds. Not really. Let's talk about what it actually was. James Watt was the one who discovered this, and what he went through and calculated out mathematically is 550 pounds moved 1 foot in 1 second. So you get a horse, lifts up 550 pounds, lifts it up 1 foot in 1 second. That's 1 horsepower. This 33,000 is 550 times 60. And that's where that number comes from. Because this is figured mathematically, it's going to be calculated on a dyno. Not everybody's dyno is the same. They're not designed the same. The mathematics, you can take one car, put it on one manufacturer's dyno machine, it's going to come out with X number of horsepower. You put it on another dyno machine, it's going to be different. So this isn't an exact science on there, but it is going to be ballpark. I had heard that in Europe, they don't measure in horsepower, but they actually measure in kilowatts. So I went on a Volkswagen website in Britain. I wasn't in Britain, I just found a Volkswagen dealer there, and got one particular model and went to look up the power, and sure enough, they had it measured in kilowatts. If you get to looking at that and you come across it, here's your number. 1 horsepower equals 746 watts. I'm putting approximately in there because, again, it's not an exact science, so you're going to come across some variations to that, but it's ballpark. It'll get you there. I found this picture of the then and now. Had to put it in there because I like that picture. Liquid and gas, primary difference here, gas is going to compress, the liquid will not compress. They're both able to flow. They're both going to put pressure out in all directions. When you pressurize it, you heat them up, they're going to expand. Back to our atmospheric pressure. So looking at this one more time, 14.7 pounds per square inch at sea level. That is the weight of the atmosphere based on gravitational pull, drawing it down. As you start going up in elevation, atmospheric pressure will decrease because you have less atmosphere above you. Ways that it's going to be measured, pounds per square inch, we already talked about that. I came across this number, the 14.696 instead of 14.7, and I'm guessing that this is the actual weight of the atmosphere, and they just round it off to 14.7. We also have a bar. Now, 1 bar equals 14.5 psi. For decades, I taught that wrong because I thought 1 bar is 1 barometric pressure. That would be 14.7. I then found out I've been lying for a long time. So 1 bar is 14.5 psi. 1 atmosphere is actually 1.013 bar. These numbers right along here, these are all the same pressure, different ways of measuring. So 14.696 psi is 1.013 bar. Also measured in inches of mercury. On the barometric scale, atmospheric pressure is 29.92 inches of mercury. Careful with the inches of mercury because we're going to talk about measuring a vacuum, which is also going to be measured in inches of mercury. However, it's a backward scale from this barometric scale. European manufacturers like to measure their pressure in kilopascals. 101.325 kilopascals is the same as 14.696. Over here, 101,353 pascals, I took the abbreviation away, is the 14.7 psi. 6.89 kilopascals is 1 psi. Kilopascals I don't have memorized. If I have to deal in kilopascals and I need to understand, I gotta sit there and look it up, because that's not one that I deal with. I will usually use the other scale that's on a gauge. When you're measuring pressures above atmospheric, you're going to use a gauge like this. This is reading 0 here. However, we have 14.7 pounds per square inch if we're at sea level. These gauges only measure pressures above atmospheric. So this is going to technically be PSIG, or pounds per square inch gauge. So just keep in mind when you're measuring pressures, you're always only going to measure pressures above atmospheric. Temperature, colder it is, the denser the air is going to be. The reason I kept this in here is because your car runs better on a cold day than it does on a hot day. When you get the air going in there, the colder it is, the denser it is, the more air you can pack into the cylinder. That's the reason on a forced induction engine, they're going to put an intercooler on there, because as it went through the compressor, it heated it up. They want to cool it back down in order to get the performance. Vacuum is not the absence of pressure. Don't get that as a definition in your mind. The definition that I want my students to remember, a vacuum is any pressure that is less than atmospheric. Looking over here on the left-hand side, this is our atmospheric pressure. On the PSI, down here 0 is going to be a perfect vacuum, no pressure at all. Then we have 5 psi. Even though we have positive pressure, it is less than atmospheric. That's still going to be a vacuum. 10 psi, and then we get to 14.7 psi atmospheric pressure at sea level. Getting to PSIG, starting off at 0, because I'm measuring only pressures above atmospheric, I have 5 psi, 10 psi, and then 14.5 psi. The reason I went to 14.5 is because that's 1 bar. 0.67 bar is going to be 10 psi. 0.33 bar is 5 psi. Manufacturers are using the bar measurement for our GDI systems because the fuel pressures are so high. You're going to find a system that's running 100 bar, 150 bar, or even 200 bar. I think if somebody knew that they had this highly flammable gasoline at almost 1500 psi under their hood, that it might scare them into buying something else. So they're going to give it to them in bar, where if they hear, hey, there's 100 bar, they're not going to think anything of it because they have no idea what that means. Now, here in the center, we have our barometric scale, which is going to be measured in inches of mercury. Perfect vacuum, 0. 10 inches of mercury is 5 psi. 20 inches of mercury is 10 psi. 29.9 inches of mercury, atmospheric pressure is actually 29.92, is our 14.7 pounds per square inch. Here's our vacuum scale. This is the one that you will use when measuring vacuum on a vehicle. It is inches of mercury also, however, it is backwards from the barometric scale. Perfect vacuum, 29.92, no pressure at all. I get up to 20 inches of vacuum, that is the same as 5 psi. 10 inches of vacuum is the same as 10 psi, and then 0 inches of vacuum, atmospheric pressure. This is the one I want you to lock into your mind. the 20 inches of mercury because cars typically idle somewhere between 18 and 22 inches of mercury. Car sitting there running, or the engine sitting there running, no load, typically going to be 18 to 22 inches of vacuum. That's how much pressure is in the intake manifold, which means at idle you typically have 5 psi. Looking at this drawing of this manifold here, we have our throttle, which is going to create a restriction. 4 cylinders here. When the intake valve opens up, piston that's on its way down is going to create a cavity, create a vacuum. We're only going to have 5 pounds of pressure to fill up that cylinder. Obviously, it's not going to do a good job of filling it. However, there's no load on the engine, so I don't need it to do a good job. It's going to get enough air fuel to keep the engine running. Come up here to the throttle. If you start slowly opening the throttle, your mind is going to think that, okay, I'm removing that restriction, so atmospheric pressure is going to increase. However, put a vacuum gauge on there. Start slowly opening the throttle. If you snap the throttle open, yes, vacuum's going to go away. Slowly open the throttle. What's going to happen is we're going to start having more air coming in there. When the intake valve opens up, more air and fuel is going to go into the cylinder, creating more horsepower. The engine RPM is going to increase, and it's going to level back out at that 18 to 22 inches. With no load on the engine, that's where we're going to be, is about 20 inches of vacuum or 5 pounds of pressure. Drop the RPM back down to idle. Automatic transmission, drop it in gear. Set the park brake. The crankshaft's not spinning free. Now it's going to try to spin the input shaft, which is locked up in the transmission, so it's going to be fighting against the friction inside the torque converter. Start to open the throttle a little bit. Crankshaft is going to try to start spinning up. However, it's going to be fighting against the friction in the torque converter, so RPM can't come up, which means the engine's going to be trying to work harder. Manifold pressure is going to start coming up, increasing the amount of air and fuel that we're getting in the cylinder. Manifold vacuum is a direct indication of engine load. That's the reason the manufacturers are putting MAP sensors, manifold absolute pressure, on the engine, because they can look at how much pressure is in the intake manifold and they know how much work the engine is doing. Vacuum, any pressure is less than atmospheric. A Venturi vacuum, again here, this is the style you would most commonly find. Moving a volume of air through this restriction has to speed up. It's going to slow back down. It's going to create a low pressure. The more air that's moving through here, the greater vacuum it'll create, which means you can put a vacuum meter right here and you can calculate how much air is flowing through there accurately. This was on the carburetor. So when they talk about a 4-barrel carburetor, there was 4 Venturis. This low pressure as the air is going into the engine would draw the fuel in. Today, we very rarely use the Venturi on engine performance, but it will come up a couple times as we go through this on later videos. Venturi vacuum, created using the Venturi principle. Manifold vacuum, a direct indication of engine load. So for my students, if I ask you what's a vacuum, it is any pressure that is less than atmospheric. What is manifold vacuum? A direct indication of engine load. On one of the job sheets that I can have my students doing, one of the questions on there is, what is the spec for vacuum? In the days of the carburetor, the manufacturers would almost always give you that. Today, you can't find it. The manufacturers do not provide a spec for you. So you're going to put 18 to 22, and the source of your information is Howard. Ported vacuum is another one that, again, it's very rarely used today, but we will talk about it on occasion, and the manufacturers would put a small hole or a small port just above the throttle. When the throttle is closed, this is above the throttle, exposed to atmospheric pressure, no vacuum. When the throttle begins to open, this is now exposed to manifold vacuum, and so you get a manifold vacuum signal here with the throttle open. They would operate the EGR, the exhaust gas recirculation, during cruise, not at idle. So the EGR, the early EGR systems were port vacuum signal. The evap system, we want to purge the evap canister during cruise, not during idle, so they would use a ported vacuum signal for that. For definition, ported vacuum above the throttle, manifold vacuums below the throttle. Alright, that's all that I've got for this presentation or this video. I hope that helps. I hope you've got a handle on what is vacuum, atmospheric pressure, and what manifold vacuum is.